So where did this come from? Why Scrum? What got me into this topic? As Michał said, I work on MongooseIM, which is this messaging backend implemented in Erlang using XMPP, and it uses SASL for authentication. And one day, little before the pandemics, there was this community request of some people saying, yeah, more security authentication mechanisms. The default on XMPP was using SHA-1, but we know that it's weaker and there are betters and so on, and deprecations. So I got like interested because it's like my thing. I like this kind of stuff. I implemented some stuff, improve according to directives that I will get later in the presentation. Then I saw that it became a CI load. Our CI was failing from out of memory or getting incredibly slow. Load tests got very polluted. So I got very curious and made more investigation and ended up with like lots of ideas in my head, some code written. And too long didn't read. The message of this presentation is don't reinvent the wheel. Use the upcoming library that I will present for SCRAM and PBKDF2. More about those two keywords later on. They are, spoiler, they are nifs. That's why they're going to be 10 to 20 times faster than any possible Erlang code you can write, and they consume constant memory. Any possible Erlang code is going to consume memory of the size of the challenge. I already said a lot of stuff that you may or may not know. What are they? Let's get to them. So let's create SCRAM. SCRAM, it's an authentication mechanism. Let's start from the end of the acronym. So salted challenge response authentication mechanism. So this cannot even be called authentication, right? You want to prove that you are you to a server and use your resources and so on. So you go and say to the server, hey there, it's Alice. Can I have access to my resources? Now, obviously, right? Server is like, pardon? So you need to prove that it's you by something that you are or you have or you know, or a combination of all of them, multi-factor. So you would usually go with a password. A bit naive. Hey, this is me and this is my password, and the server is like, I check. Yeah, that's you. Okay, good. Yeah, okay. That's very naive. You all can see why, right? Like there is somebody in the middle here listening. He got your private password and he can just log in as you in the future and just steal all your resources. Not what we expect from authentication. Okay, improve the flow a little bit. Put it on a secure channel, TLS, for that matter. Very good. Seems very promising, but it could have a couple of pitfalls. The first weak point, the most complicated one, but very legit, is man in the middle. TLS is quite unbreakable, so to say, for confidentiality and forward secrecy and authenticity and all of that, but authentication in the TLS level is the weaker part of TLS. It's all this trusted change of certificates, and it has some DNS spoofing as that where you can attack it. It gets tricky. So then the big brother is listening to the whole communication. Another weak point, storage. Like the server has to check that this password is the correct one for this user, is stored somewhere, and the attacker, big brother, whomever it is, can just get the database, and voila, we're lost again. And another weak point, you can just try hard. You can just connect to a server and say, hey, attempt number 1, attempt number 2, attempt number 3, number 4, and so on and so forth until you get it right. A problem with the brute force weakness, and it's a problem that we are going to see very often, and this is a very basic problem when you get to cryptography, is what is called timing attacks. You know, you provide a password, the server has his password, and the server has to compare them. And more or less every typical implementation of this binary comparison in just about any language, Java, Python, Erlang, and Elixir, you name it, you usually do it the most performant way. So you compare, you have two binaries, you compare byte and byte, they are the same, okay, next byte, they are the same, okay, next byte, they are not the same. You don't need to go to through a very long binary. If byte number 3 is already different, you can finish your operation and make it faster. But this is really bad for cryptography. In cryptography, all operations should take the same time. If you do this, you can just as well guess by the time it takes to answer how many bytes you have guessed correctly. So you send a request, it takes 1 nanosecond, you send another request, it takes 1 nanosecond, you send another one, it takes 2 nanoseconds. Oh, I got 1 more byte, correct. And so on and so forth until you build a whole bunch of bytes. This is really realistic. This is something that has happened. Like Java 6, for example, had this message digest is equal implementation that was leaking this kind of information on the standard library for Java 6, long time ago. OpenSSL back in the very beginning of time also had this kind of issues. Python had some similar libraries, keychar, which is not alive anymore these days, but it's a beginner's mistake, and it happened to professionals at the beginning of this movement of cryptography. So that's something to take care of. Okay, some solutions to all these issues that we saw: the storage, the timing, and so on. Store hashes, transmit hashes, hash everything. Let's get through these solutions one by one. Store hashes. Okay, so first thing, let's not allow the big brother to steal the database. You store the hash of the password, and if he steals the database, he gets this big bunch of binaries. Has no idea what was the password supposed to be. Hashes are supposed to be irreversible. They are one-way functions, so you cannot get back the original input. And just as a comparison, you get here how would it look, for example, for SHA-256 of Wonderland, and Wonderland where you just change the L by a 1. It's a completely different thing. Okay. Transmit hashes. Like if you steal the traffic, you can still see the password. So transmit a hash of the password, and then again you get this big thing, and you cannot recover the original password. Hash again before comparison. For the timing thing, imagine that you correctly guess 1 byte. The structure of your input has nothing to do with the structure of your output on a hash. So if you submit an attempt of Wonderland and it takes so and so many time, and then you submit another attempt where you change the next byte and it takes a little bit longer, it doesn't really tell you anything because you have no idea what changed in the output of this hash. So the server just makes a construction that breaks any possible structure of the submission. And then you can do your quick hash comparison, your quick binary comparison. Okay. Another way, fix the channel, communicate over secure channels and bind to it. So secure channels like TLS, they have some internal secrets that are negotiated during the whole establishment of the session, and they are unique to this session, and only the server and the client know this secret. If there was to be a man in the middle, this man in the middle will for sure have different secrets in the 2 endpoints. So if you use that knowledge to mix it a little bit with your password, you're going to generate something else. And the server will just do the same and generate hopefully the same thing. And there is no way that the attacker can undo one and redo the other. So as I say, the man in the middle will for sure have a different secret here. Note that the code provider will never repeat. This is unique because that's a purpose of that's what TLS does on this level. This session secret is different. There are different session secrets for TLS 1.1, 1.2, 1.3, and so on and so forth. If you didn't have channel binding, you didn't have access to the secret and so on, you may just put a static value there, and just so you don't change the protocol. Like you always provide some session secret, but you don't always have it. So if you don't have it, just put a static value. Okay, fix everything at once. The hashes. Okay, so you hash the password, you mark it with the secret, and you store the hash that you retrieve, and you compound all the solutions that I just mentioned all at once. Okay, hash versus MAC. Point to make why you are mixing these your password with your session secret unique for that session. You are using for that a MAC, not a hash, because hash are used to guarantee the integrity. So if like somebody tried to change the input, the output will be a completely different thing. But you can as well just change both the input and output, and then the combination is valid. So you need to add a little bit of secrecy there and this MAC construction, and then you know for sure that the output cannot be tampered with. So the output is going to be authenticated. Usually a bad MAC is just using the hash of concatenating the secret and the public data. The secret is your password, public data is the TLS secret. It's public because both endpoints have it. And if there was to be a man in the middle, he has all of them. So it's like public for all purposes. And the secret is the password. This would usually be a bad MAC. It's a naive one. It doesn't work for all possible hashes. For some of them, yes, some no. Most often don't do it that way. Usually HMAC is used. It's the most popular MAC on the internet. Okay, so process in simple steps. The client sends a hash and marks it with the session secret. The server receives that, retrieves from his database the hash, and then he also has the session secret, builds the MAC, and does the comparison. And we can go for the naive binary comparison, because they're going to be different on every submission. So you lose any structure that you can be able to guess. Where are we standing now? Hash everything. Okay. Now, next problem. Human passwords have low entropy. So the final hash is going to also have low entropy. So, okay, you cannot undo the hash and you cannot guess by hashes because they are too big and there are too many trillions and trillions of possibilities, but you may as well just try all possible human passwords, hash all of them, and then get that comparison. And then from the many trillions and trillions of possibilities of hashes, you actually have a couple of millions because humans don't use that many passwords. So some attacks that you can do is, of course, go online and try again and again. Most often you would do an offline attack, capture some packet, get the hash, and try to just compute all possibilities. You would often use these reduction tables. This is a rainbow tables where you like pre-calculate intervals, so you don't need to calculate all the hashes of all the possible passwords. It's a trig and a trade-off space computation, or you can as well, for a bunch of rules, compute the hash of all the conversions. An example, like as Michał said at the beginning, I was born in Venezuela, but you know, I grew up in Europe, I live in Europe, and maybe like most people don't know that I was born in Venezuela. Maybe it's a secret. Only if you see my passport, you see that it's written. Imagine that my password for whatever service is Venezuela, right? So you can try the hash of Venezuela. Calculating a hash is very fast these days. Then does it work? No. Okay, just calculate the hash of Venezuela, but the V, use the first V instead of lowercase, make it uppercase. Doesn't work. Okay, the E, the second letter, just swap it by a 3 because that's a common pattern that humans make, and so on and so forth. Maybe inject at or a exclamation mark at the end. It's not that many combinations anyway, so you can just try all of them. And there is actually specialized software in the open source, super optimized for GPU, to try all these possible human passwords with all common conversion rules. And in that couple of GPUs for $1,000 that you can buy, you can try a few billion of hashes per second. It's super specialized. So next thing that we need to do, to first of all avoid these pre-computed tables, whether they are rainbow tables or dictionaries. That's the first thing we're gonna build a defense for, is adding a salt. So a salt is a cryptographically randomly generated value that is long enough to add enough entropy. At least 8 bytes is required by most of the standards on the internet. Very often they advise 16 bytes, NIST or many other RFCs implementing authentication protocols and so on. So you generate this salt, you can consider it public as well, as it continues being public data, and you mix the password with this salt, this crypto random secure, very, very random, and you mac it. You use your password to mac the public data, the salt, and then you build this new hash. And every client is going to have a different salt. So, and you don't know what that salt is, and that is cryptographically heavy. It's a truly random, I recommend 16 bytes string. So you would, if you wanted to pre-compute anything, any dictionary or rainbow tables, you will have to pre-compute all possible combinations of passwords with all possible conversion rules for all possible salts, and there is a hell of a lot of salts. So you don't do this pre-computation anymore. It's absolutely unviable. And again, we use MAC and not hashes to ensure that the password was not tampered with. And in the database, you store together with the user the value of the salt. And Big Brother is a little bit sad here. It's like life is not going well. You can see in the top the output of SHA with Wonderland and the HMAC of Wonderland with just 1, 2, 3, 4, 5, 6, 8, 7, 8. And you see that is, again, completely different thing. So now the attacker can only try hard, real time. You can just compute billions of hashes for all possible combinations of password, salt, and conversion rules. He can still try. It's, you know, GPUs, you for $1,000 you buy really good specialized hardware, FPGAs. So just try. So make it very hard to try. Next defense, we continue building layers here. So the client says, can I have my salt? The server checks the DB. Ah, yeah, this is your salt and your challenge. So together with your salt, now you have something to do. The client follows the rules of this challenge and submits that together with the salt. And that's what the client sends to the server. And then the server can make this comparison. The server also has the output of this computed challenge and so on. We'll see the computed challenge in a moment. Now the big brother or attacker or whomever it is like very sad because like he has been like prevented from doing his job in a lot of layers now. Let's continue building layers. One more step, sign the challenge. As we said before, the channel secret, the TLS channel secret, is unique for a session. So if you have that data, you mix it with the whole salt challenge and so on and so forth. And what you generate that you're going to send in the end is unique to that session. So next time you actually have to generate a completely different thing. So you prevent replay attacks. If somebody manages to steal a packet from an authentication, that is useless the next time because there is entropy that is unique to that session in what you are sending. But if, for example, you don't have this TLS secret, you may as well just generate it on the application layer, not necessarily extract them from the network layer. And this is what is called nonces, which is something that you use only once. The client generates one, the server generates one. They are negotiated pretty much in a similar way that TLS does it on the network layer. You just do it on the application and so on. And if you have channel binding, use both. If you don't, you can just use this nonces. And again, these nonces are generated like the salt, cryptographically secure, randomly generated binaries. Most often 8 bytes is the requirement by the standards. You can as well use 16 and mark it with the secret. And with that, you generate a one-time pad. We'll see how you use a one-time pad in a second. One-time pad, by the way, also the acronym OTP, but it's not the OTP from Erlang, it's a different OTP, is the most secure crypto primitive you have. Just store it. One-time pad is just storing whatever you have with your super secret random thing. And it's the safest you can have in cryptography as long as it is a one-time pad. If you ever use it twice, it's not safe. It's absolutely broken. You're screwed. But if you use it one, it's the best. So we made it to use it once because we have been adding a lot of data that is unique to this session, like the session secrets, the nonces, and so on. Okay, So you have your unique data, nonces, session secrets, you have your client key where the client compute his challenge, you store the hash of that thing, and the client builds a signature that he has this knowledge, that he knows that he has this password. The client will use all this unique session data to map the actual secret and send it to the server. And this session secret will be used as the one-time pad, the SOR, and pad the client key and send it to the server. And then the server will also have the client signature, so he can undo the SOR and then do the comparison. That is a SCRAM. We have just designed it. And you have seen all the layers that we have been building, all the steps of security that we have been adding, what we defended for in the storage, on the channel for man in the middle, the size of the challenge and how much lower it's going to get to compute every attempt. So this is a quick overview again of what is SCRAM, everything that we have just designed. The server stores only, no, I don't want to go there. The server stores only the salt and the iteration count. The challenge is going to be described by a number of iterations, and the stored key. And the stored key is this thing. This is the hash of the HMAC of the challenge. In the SCRAM terminology, this high is how the challenge is called. You normalize the password and you mix it with the salt, the iteration count, you generate your salted password. You use this static value client key. They can be public, that's fine. To map, you use your secret to map that public value that is static, then you hash that. This is what the server has. The client also has, and the client computes all the stuff that we use. So provided the salt and the iteration count, he computes the password, the client key, the stored key. He has all this authentication message that is a build-up of everything that you have been exchanging, nonces, TLS session secrets, etc., etc. From these two, as we saw before, you generate the signature, and with the signature, you can SOR one-time pad the best you have, the value that you're sending, you send that, server undoes, compares. And one more thing, the server may as well prove that he has the stored key. Otherwise, you know, it can be a server that just accepts anything. So the server will, like, if you see the client is sending is storing the client key, and then the server, when the server gets that from the client key, he can compute the stored key, but this server will send back the stored key, also stored with the same one-time pad. And then the client knows that this server is the server that is authenticating. SCRAM, thanks to a blog, you know, I spent lots of time reading and learning myself how SCRAM, and I discovered just about every second blog on the internet about this topic, and there was this one with really good ASCII art. The challenge. What is the challenge? So it looks like this. You have, it's going to be called PBKDF2 because number 1 is totally broken, so just number 2, which is a password-based key derivation function. Version 2 that has 2 parameters, the key derivation function that is using inside HMAC and the number of times it's going to apply it. And it applies so this way. HMAC takes this secret value. Sometimes my pointer disappears. HMAC takes this secret value and the public one. It uses the secret to authenticate or to prove the integrity of the public value. And it generates this output, and this is used as the public value of the next HMAC. So the password you use always the same on all the rounds, but the input is the one from the previous round. So it's not parallelizable. And then all those inputs, as you generate them, you're also storing them. And this is the derived key. So an overview, the client starts, he sends his channel binding data, his username, and his unique nonce. The server sends back his unique nonce, the salt and the iteration count for this client. The client has all the data he needs. He computes his huge challenge, Mac, soaring things, all that stuff that we saw. Sends that to the server. Most importantly is here, the last part. Client key sort with a signature, and the server can undo the soaring because he has this one-time pad. And this one-time pad is generated uniquely per session, so you cannot replay it. The server sends back the soar of his stored key, and the client knows that this is also the server that has his authentication values. Or an error, the server says, no, you're not authenticated. So implementing SCRAM. The problem, it's obviously expensive. That's the point. It's a challenge. It's going to be very expensive. That's what we build. So first of all, when you have this on CI, set the iteration count very low to 2, just for integrity reasons. But that's all, because otherwise you will see GitHub Actions, Travis, Jenkins, Circle CI, whatever pipeline you're using, just suffering because this is expensive. Load testing gets polluted. Suddenly your load test got dirty. You don't have no idea where. And yeah, your system is spending lots of time calculating things. And for God's sake, if the client can just ask the server to do any challenge he wants, then it's like screaming, please DOS me. Like it's a denial of service. You don't easily allow the client to make these requests. And they should not be the most expensive thing. You want them to be as cheap as possible for the server. So a little bit of background. One-way compression function. Let's talk about cryptography for a second. One-way compression function has 2 inputs. One of them is of a fixed size. The other one is arbitrary. They are mixed in this magic box. Whatever the algorithm is, there are many of them, and they can be very complicated. And there is an output of the size of this init value. So it's compressing a lot of data into something smaller. It's almost like a hash function. It's just missing one thing to be collision resistant and a cascading effect. The Merkle-Damgard construction is a way to build a proper hash function from that compression function that we saw before. And MD5, SHA-2, all of them, they are built from this Merkle-Damgard construction. So you define your F, your compression function, that needs to have this and that properties and so on. And then you define the padding to your algorithm. You define the sizes where you're going to chunk your input, some initialization vector that is also static and defined by your protocol. And given all those parameters, you just put all of them like Merkle-Damgard says, and you get a construction that does what a hash needs to do. And this is how SHA works. SHA-1 and 2. SHA-3 doesn't work like this. So, you know, just choose all your parameters. Message authentication code, as I said before, it proves, a hash proves only the integrity, but the MAC proves the integrity and the authenticity. It does not prove confidentiality. That's what TLS would do. They are produced to design, they are designed to produce matching MACs only if the same message, secret key, initialization vector, and everything is exactly the same. Key derivation function is a function that, given an input, derives a new output with new properties from it, using cryptographical primitives inside, and is most often used to stretch into longer keys. You know, a human password is how many characters Venezuela has? 9. I hope I counted correctly. I'm just guessing this live. So 9 characters is not a lot of them, but you may, you know, the hash is going to have 20 something, so it's expanding them. And they are going to have better properties, more entropy, bigger sizes, and so on and so forth. HMAC, which is the MAC that we have been using all along. It's like this. So SHA of key appending message suffers from length extension attack, so you don't want to do that. There are plenty of libraries as well to take advantage of this vulnerability, so careful. what you would usually do is this construction that is a double SHA, so to say. So you get your key stored with an inner padding. This is a static value defined by the protocol, appended to your message. And then if you remember from the Merkel-Damgard construction, you have a bigger input that you're going to chunk and run the compression function in pieces. So this block here is actually as if it was just SHA and nothing else. And it's going to have just two, the size is going to be of two chunks. That's also something that HMAC is pre-doing. If the size is not of the chunk, it will just hash it according to SHA-1 to whatever it's using underline to make it of the size. So the input is going to be two blocks, and one of them is going to be key stored with the inner padding, and the other one is going to be the message. And then there is another SHA of the key stored with the outer padding, and the message is the output of the previous round of SHA. That's HMAC. The PBKDF2, the construction that we saw before, that's the challenge. If, as we saw before, you have an HMAC, that the output, you plug it into the next HMAC and the output to the next, and you pipe all that stuff. And now you have n iterations, let's say 10,000. It's a common number. iOS, Android are usually advising 10,000, many other phone environments. For phone, the usual agreement is 10,000 because of the phone is not going to have the same performance than a computer, and so on and so forth. How many times? You have 10,000 iterations. How many times you are going to do the underlying compression function? Remember, HMAC is doing 4. And you have 10,000 HMACs. Sounds like intuitively you're going to have 10 for 10,000 per 4, 40,000 compression functions, right? Sounds intuitive. And this is actually how the RFC for PBKDF2 is described. But this is something that it's not like this. This is something that every attacker code has right, because attackers, this is their job and they always do it right, but defender code don't usually have it. OpenSSL didn't have this optimization up to 09, forgot the number. There were plenty of Java 8. There was some library in Java 8 that was also implementing PBKDF2 the naive way. More Python libraries, plenty of them. Open, BSD, SSL, don't remember the name of this library. A BSD equivalent of OpenSSL was also doing this wrong until like 2 or 3 years ago, and so on and so forth. Is half. Why? Because this half of the HMAC is always the same. The initialization vector is the one of your SHA, the underlying SHA that you're using. The inner and outer padding, they are defined by the HMAC protocol. And the key is the same for all those runs that you're going to do. So this half is going to be always the same for your 10,000, 10 million, whatever. So you calculate them 1 at the beginning and you have them forever. That's why 2 plus 2n. And that's when n is sufficiently big, the 2 at the beginning doesn't count. It's half of the time. So how this would look in Erlang, almost wrapping up, and I'm almost done. This has a problem in Erlang. This is a typical code that you can see on the Postgres driver for Erlang, for example, that we had in MongooseIM, a very similar one. Plenty of code on GitHub I have found with having this code. On every iteration, you can see that this is just counting back, iteration -1. You are calculating the HMAC. So you don't have access to that for compression functions. You have to calculate the whole thing. And you are generating a new binary. So the amount of memory that you're going to consume, because Erlang has no mutation, is going to be linear to the size of your challenge. So you're going to generate a lot of memory. I will show you a benchmark in 2 slides. So lots of copying, complex allocation and deallocation, no cache locality. When I was benchmarking this after like 10,000 rounds, which is a very common number, you could see a lot of system calls for memory allocation. Memory, yeah, mostly the memory is what suffers, and algorithm is 4 of n. So the solution implemented as PBKDF2 was designed for in C, C++, Rust, whatever. I implemented it in C, taking some parts of it were already implemented in an open source project. So I just made some adaptations and plug it into an if. So access to the compression function. So half of the time use some fancy time slicing and if scheduling. So everything runs fantastically on the beam. We are using it in MongooseIM. So we have tested it in production. And it would look like, yeah, just call your C code. It's very highly optimized, lots of inlining, lots of tricks there. And the benchmark will look something like this. So this is a comparison between this code that I have written and a hex library for Elixir, that is the most downloaded one in Elixir. And the previous code that I showed you in Erlang that lots of projects have it just hard-coded in their source. And you can see that the biggest difference is in memory consumption. Like you see the difference. Like the Erlang code is this Elixir code was like really, really good. It's the best you can have in pure Beam. And I'm pretty confident. And this gets even worse when you go to 1 million iteration counts, which is common for password managers, for example, or like more security heavy environments where memory just really gets crazy, but fast PBKDF is still using the same 0.000 and a few bytes, like less than a kilobyte, like half a kilobyte or something like that was. And there were more hex packages implementing this thing and some projects implementing in-house their own code that I also benchmark, and the results are way, way worse than these three. So like if you want to do this, if you don't like the NIF, use one of these, either the Erlang or the Elixir one. They are the best I could build and find. Then otherwise, go for the most optimal code. And that's all from me. Here you have some links or where you can find this code and you can check it, submit pull requests, verify, test, and so on. They are published on Hex, both PBKDF, if you want only this challenge, and SCRAM, implementing the whole SCRAM protocol, parsing, flags, and everything SCRAM. And where do we use it? In MongooseIM. And that's all. That's all from me for today. Do we have any questions?
So we have time for one question, and if Derek Sweet can join us, maybe you can ask your question on the stage. Derek, are you with us?
Yes, I'm here. Can you hear me?
Yes.
Great. Yeah, well, I just at the real we switched all of our auth over to Okta, and I was wondering how you felt about outsourcing auth to services like that, and if you felt there were any big advantages to managing one's auth other than not having to pay for it.
Yeah, that's the usual question in programming. You know, trade-offs. You gain this, you lose that, and so on. For example, one thing that I'm reluctant as a user, not as a programmer, but as a user, when I go to some service and says log in with your Facebook credentials. No, Facebook knows too much about me. So it depends on who is that provider. And also the API to that provider uses some global keys that your server has. So that is a layer, a surface of attack that you have a lot of control because it's in-house, but the value of losing that key is way more expensive than the value of one client losing his password. Then it's way worse for the server to lose that key. On the other hand, it's way easier to protect it. Yeah, it depends on what you're doing. It depends on if you trust this second provider, on how much you can defend either your database or this key for the API with your provider. Also, sometimes this OAuth I think that most often they are authenticating with JWT tokens or some equivalent. And again, these tokens have some problems. There is plenty of materials on the internet on what is wrong with JVTs and what is good. Not get me wrong, they are very good, but they have a lot of things that are also bad. No protocol is perfect. So it will take me an entire other talk to like compare all the pros and cons of outsourcing, insourcing one kind of encryption or the other.